Hey gang! So in today's video we're going to talk about various measures of dispersion or spread in a dataset. Our main way to measure this is with what's called standard deviation, but we'll also touch on the range and variance of a dataset. Let's start with the range. Pretty quick on this one. It's just the difference between the largest and smallest values. So with this example, we saw this data in the previous video. If we want the range here, it's sort of the distance that the data set spans. So the biggest value minus the smallest value gets us 11. So this data set spans a distance of 11 units. Standard deviation is an important attribute of statistical inference that we will see over and over again in the later sections of our course. And it's probably the most common used measure of spread in a data set. And we'll kind of dissect what goes into standard deviation. There are two versions. There's a population version and a sample version. And you might remember that the population version of the mean applies, well, to the population, and that would make it a parameter. And so usually this is unknown, because we don't typically have access to populations. There are exceptions. Over here, when we collect a sample from the population, then this is some descriptor of the sample, which makes it a sample statistic, which is known because that's the point of collecting a sample, is to collect info from it. Now we're going to look at both of these. However, it is the sample standard deviation that will be of primary focus in our course. So I'll put a star over here, but we are going to look at the population version today. Let's look at the notation and the formula. The population standard deviation utilizes a Greek letter because it's a parameter, and it's usually the Greek letter sigma. That is lowercase sigma. It kind of looks like a 0 with a little handle on it. And over here, the standard deviation of a sample usually just is represented by the letter S. Let's look at the formula now. The formulas for these are nearly identical, but there is a distinct difference. Let's start with the population standard deviation. And I like to do this a little backwards, so if you're taking notes, give yourself a little space over here. Deviation. In the sigma notation video, we talked about how a deviation is a distance from the mean. And we're talking about spread in a data set. So the standard deviation starts with your observations, and you subtract the mean. But because this applies to a population, this will be the population mean. If we were to add up all of those deviations, you might remember that this would always add to a 0. So we sort of get away from that. We take the squared deviations. And this is called standard deviation. Standard, like typical, like average. Right now we've got squared distances from the mean. If we were to divide by the number of observations in that population, this would be like the average squared distance from the mean. Usually we want our parameters and statistics to be in the same unit of measure. So right now we're in a squared world, and you know what undoes a square is a square root. I would like to annotate this formula here so that all the letters and symbols are defined. Capital N, that's a capital N, that would be the population size. Mu, that's that Greek letter, that's the population mean. And we saw yi was data. Cool, so a really nice way to interpret this statement, this is just a number. You plug in numbers and you get a number out. A really nice way to interpret it is as the typical distance from the mean. And we're going to hopefully illustrate that with an example here shortly. But before we get there, I think I will also write the formula for the sample version, which is the one we will mostly use, of the standard deviation. So just so this is all in one place. So this is represented by the letter S, and it has almost all the same elements and structure as the population version. We're going to take our sample observations. We will subtract the mean of the sample, which would be y with a bar, and then square those deviations and add them up. The main difference here is that instead of averaging with the letter n, we actually do n minus 1. Again, these are squared deviations, and we get back to the original unit of measure by square rooting in our final step. This sample version, again, is going to be the one we're going to focus on in our course. So I'm going to put this one in a big old box to list all the symbols and letters used here. It's going to be the same concepts but applied to a sample. Lowercase n is the sample size. We are taking deviations from the sample mean, y with a bar, and yi is the data yet again. I guess I can put that in here. So now I would like to run through a couple examples to illustrate how we calculate standard deviation. Okay, I'm going to actually do sort of a comparative set of examples here. Let's consider a population, and it's a small population. I'm going to call it population number 1. And let's suppose that it consists of these 4 values, 2, 2, 3, 3. All right. And let's compare that to this other population over here, pop number 2, also consisting of 4 values, 0, 0, 5, 5. I would like us to guess or estimate the standard deviations of these populations with a little bit of guidance. Now first, let's compute the mean of these 2 populations. It might not be too difficult to see that it's 2.5, or if you add all these values up, they add to 10, 10 over 4, 2.5. And that's the case over here as well, right? Population 2 also has a mean of 2.5. This brings me to another point, that the mean, or a measure of center alone, is not enough to give you a lot of information about what's going on in a data set. because certainly these two populations are different and have different behavior, but they have the same mean. So knowing the standard deviation gives us another element of knowledge about what's going on in the data set. It's a summary. Now, with a little bit of guidance, let's see if we can estimate the standard deviation of the first and the second population. Now, I've got my little phrase up here, typical distance from the mean. So what I would like to ask you is, we've got our 4 values here, and I want to consider, well, how far away is 2 from its mean? Isn't it 0.5 away, right? And how far away is 2 from its mean? Again, 0.5. And how far away is 3 from the mean? 0.5. Each value in this population is 0.5 away from its mean. Typical distance from the mean. Can we guess then what is the typical distance from the mean of this population? My guess would be 0.5. And maybe we'll put a question mark on that. We'll prove it with a calculation, but this is where our intuition has taken us. So that's kind of fun. Let's do that again with the second population. Now, before we start going through this little rigmarole, does the second population, does it appear to have more spread or less spread than the first population? It's more spread out, right? These values have a range of 5, right? 5 minus 0. These only have a range of 1. So population 2 has a bigger range, but also 0, 0, 5, 5 is certainly more spread than 2, 2, 3, 3. These are kind of clumped on the mean. Let's run through this procedure here to guess what the standard deviation of this population is. Again, how far away is 0 from the mean? 2.5. That's the case for both those zeros. And how far away is this 5 from the mean? 2.5 again. What would be a reasonable guess for the standard deviation? Probably 2.5. Awesome. So that's kind of the backbone to standard deviation. It's the typical distance from the mean. Let's go ahead and compute the standard deviation of this first population, okay? Let's compute standard deviation from the first population. Okay, I've got the formula up there. It's still slightly visible. The square root will be the last operation, but I don't want to forget it, so I'm going to write it down. And that might be enough. The second to last move will be the division by the population size. There were 4 values here, so that would be division by 4. The bulk of the work is going to occur in this sum of squares. I'm going to open up a big old set of parentheses here. There's going to be 4 quantities added. Those quantities are going to be squared. And what is going in these parentheses is your data. So that's going to be the 2, the 2, the 3, the 3, and subtract every time the average 2.5. So I'm going to put the 2, the 2, the 3, the 3. We will subtract 2.5 each time. All right, let's make sure my square root is there. Cool. We've got all our values plugged in, and now it's time to rock and roll. I'm going to need a little more space here. Equals, we keep the square root. We're going to keep the division by 4, and we will simplify. The value in the parentheses is a 1/2. Careful, it's a negative 1/2, but that negative will get squared away. Again, this subtraction results in a negative 1/2, and these subtractions result in positive 1/2. Don't forget the square. Okay. What is half of a half? 0.5 times 0.5. Those are all quarters, right? We've got a positive quarter. Ooh, there are 4 quarters here. And we all know that 4 quarters gets you $1. So this big set of parentheses boiled down to a 1. So I guess I can write multiply by 1, although that's not required. Scroll down a little bit. And we have our guess sitting right here. I think I see it coming. We have the square root of a quarter. Just in case you need a review here, the square root of a fraction is the fraction of the roots, and the square root of 1 is a 1. The square root of a 4 is a 2, which is 1/2. Awesome. So this matches our guess. Maybe I'll even cross out the question mark and replace it with a check mark. Yeah. So that's pretty exciting. So again, this was the standard deviation of a population. I think I will skip calculating the second population's standard deviation and leave it to you for an exercise for practice. You may know the answer by now, so that can guide you. And now what I would like to do is yet another example, but for sample standard deviation. I better scooch on down here. All right, let's look at another example, but this time of sample data. And we're going to compute the standard deviation, and first we need the mean to do that. And I'm actually going to go ahead and open up R to get the mean for us. I've got an editor open here, and I'm going to make a vector. I'll call it data. And I need to string together or combine a bunch of scalar values, and we do that with the letter C. 45, 51, 55, 61, and 63. And then I will compute the mean of data. Okay, let's see. The mean is 55. That's nice. I'll also do the standard deviation of data, but not yet. We'll do that when we're done to check our work. So the mean is a 55. Write that up here. And what I'll also write up here is the formula, just so it's in our face. S for sample standard deviation, big square root, 1 divided by n minus 1, the sum of squared deviations from the mean. All in the square root. Okay, so that's just for reference. Let's go and start computing. I'm going to need a bunch of space here, so I'm going to make a big old square root sign. Might be too much. What is n here? Can we identify n, the sample size? N is 5, right? So this will be 1 over 5 minus 1. Then the bulk of the work, the sum of squares, we're going to take each value of our data set and subtract the mean of 55 and then square that subtraction. I'm going to go ahead and do that for the next values in the data set. Okay, we've done the hard part, transcribing our information into this formula correctly. The bulk of the work is going to occur in these big bracket parentheses. We're going to take these subtractions and then square them. So here this looks like a -10, 4, negative, everyone's favorite number, 0, 6 squared. I forgot the square on that 0, but I didn't really need it, did I? And lastly, 8 squared. Now we're going to add all of these up, and I think I will actually go and get R to do that for me. Okay, in R I'm going to do 10 squared is 100, 4 squared is 16, plus 0, I'll write it for clarity, plus 36, plus 64. The sum of squares is a 216, and then we need to divide that by 4. So I'll go ahead, since I've got R out, go ahead and do that right now. Ooh, that's a 54. All right, that's a fun number. Let me write down what we've got so far. We got 216 divided by 4 is 54, but now we need to square root that. So let's take the squirt of 54 and should be between 7 and 8. Awesome. Approximately 7.3485.
Awesome.
Let's check our work using R to validate our solution here. The way we would do this is with the SD function, and I believe I called my vector of data, not very creative, and we're looking for 7.34. Well, that's very satisfying. All right, we've done a bunch in this video so far, but we've got one more concept to discuss, and that is variance. We will not be using variance a lot in our course, so I will keep this brief. And I will only show you the sample variance. And it's just the square of the standard deviation. So it is denoted by s squared, and I'm going to start writing this formula that hopefully looks familiar. I've got the sum of squares divided by n minus 1, but I am not going to put the square root symbol here. because the square and the square root would cancel each other out. One reason we will not be using variance is because of the units. Let's suppose you are measuring a variable in meters, right? That is a measure of length. And here, what happens in the sum of squares is you square your meters, and you no longer have a measure of length, but you have a measure of area. So it's no longer in the original unit of measurement. This is very useful in other applications of statistics, but for the context of our course, we're going to breeze right by it. The calculation is very similar to what we've done just in the past 20 minutes. It's actually a smidgen easier because you do not need to square root. In the previous example, the solution would have just been 54. It's the value before the square rooting occurred. So anyways, that's going to do it for us in our video. See you in the next one, where we will look at an application of standard deviation.